Hey guys, and welcome. In this session we are going to talk about IMP file for UEL subroutine in ABAQUS. Why do we need an IMP file? First, we are basically introducing a new element, so generally CAE does not come in handy. Second, in every finite element analysis we have a series of nodes connecting together and forming elements. So we are going to need an IMP file to introduce nodal connection and elemental distribution. How are we going to do that? First option is that we know all the commands and formatting, so we are going to generate the IMP file from the scratch. Second and most favorable is to modify the IMP file produced by ABAQUS. In most of the times we are going to use the second way. First, we need to introduce the nodes. We are going to be in part module and node option. The first integer is going to be the node number. For example, node 1, node 3, node 5, node 4. And the second, third, and fourth is going to be the nodal coordinates. In this picture, we have a 2D analysis for plane stress. So we need only x's and y's. Next, we are going to introduce the user-defined element. So we are going to use the star user element option. Then we are going to introduce how many nodes do we need. For example, if I want to model a 4-node element, for example like this, I have 4 nodes. Then I'm going to type 4 in nodes. The third option type U1 is optional, is elements name, and properties is the properties of that element. If we are using elastic analysis, we only need the Young moduli and Poisson's ratio. Then we are going to need the coordinates of each node, which here is 2, x and y. Then we are going to see how many variables does an element have. For example, so in a plane stress I'm going to have sigma 1, sigma 2, sigma 3 and tau 1, 2. Sigma 3 is already 0, but we are going to consider it just for validation. So every element is going to have 16 variables. Next is the coordinating order. For example, node 1, coordinate 1, coordinate 2, node 2 here, coordinate 1, coordinate 2, etc. If our coordinating order is the same for all the nodes, we don't need to specify it for every node. Next, we are going to introduce the elements. My option is star element type U1 is the name of my user element. The first integer is the element number, element 1, element 2, etc. And the other numbers are going to be the series of nodes connecting and forming that element. For example, element 1 is basically going to have node 1, node 2, node 7 and node 6 and etc. Next, we are going to generate the nodes and elements. First, we are going to generate the node sets, for example 1 to 25 node sets, and we are going to have 16 elements, so we are going to generate 16 elements, and we are going to use the option UEL property LSET solid, which is here, to have the Young moduli and Poisson's ratio according to our input. Next, we are going to define the boundary conditions. For example, if we want to have supports and we are going to have some nodes that will be pushed, we are going to use the option inset. Some important notes. So we are going to introduce a new element. That being said, the visualization module cannot be directly used for showing the results because visualization is for the elements existing in the library. So how we are going to solve that issue? Option 1 is to use a dummy element or decoy element in conjunction with the UMath subroutine. That is going to be our first and most favorable option. Second, we are going to use the Python script to extract the results. I've already shown the Python scripting for extracting data from ODB files, so I'm going to concentrate on option 1. Assume that we have a 4-node element that have the Young moduli of steel and uses UEL subroutine and SVARs as output. So we are going to introduce a decoy element, for example here, which have the Young moduli with a very low number and uses the UMath subroutine and STVs to store the data and show the data. So we are going to use the UEL to generate the results, and we are going to set that in SVARs. Then I'm going to send the data from SVARs to the UMath subroutine, and from UMath subroutine I'm going to save them and store them in STVs. Next, I'm going to use the STVs in visualization module. So this is the whole trend, and we are going to see an example in the following videos. This concludes our video. If you find this video useful, please like my video and subscribe to my channel. Take care.